Hello, today we reached lecture 16 and we will continue our discussion on chapter 18, which what happens when two waves superimpose. So let me quickly remind you of what we have finished so far. So the very first thing we studied is what happens when two sinusoidal waves superimpose. But in this particular case, we took two sinusoidal waves that are identical. Okay, so what do we mean by identical? We mean that they have same wavelength, same frequency, same amplitude, and traveling in the same direction. So if two waves have these conditions, then we can find, so look at these two waves, y1 and y2, they have the same k, so same wavelength, they have the same omega, so same frequency, they have the same a, so same amplitude, and they're both minus omega t, so they have traveling in the same direction. The only difference is that there is a phase difference between them. Then y resultant, we found that it will be 2a cosine phi by 2 sine kx minus omega t plus phi by 2. And we did a question last time where, for example, we have the y resultant and we said find the phase difference, okay, or find the amplitude and we have the phase difference, different questions. So this is the very first thing we finished so far. The other thing we finished so far is the case of standing waves. Standing waves, they are also two identical waves. They have same amplitude, they have same wave number, that is same wavelength, they have the same omega, that is the same frequency, okay? But they are traveling in opposite directions. They are traveling in opposite directions. Then when they superimpose, they will cause something called a standing wave, a standing wave. Why it is called a standing wave? Because it will seem as if it is not moving. It will seem as if it is standing, okay? But in reality, it is not standing. So we will see things like this. I hope I can draw it properly. We will see something like this, okay? As if it's not moving, or something like this, as if it's not moving, or something like this, okay? We can draw many of these. We call them loops. Now, what do we have here? Here is, let me use a different color. This is the amplitude. This is the amplitude of the oscillation at each particular value x. And we notice that there are points where there is no oscillation at all. When does this happen? This happens, so no oscillation at all. When sine kx is equal to 0. When is a sine of a function is equal to 0? This happens when kx is equal to n times pi. Okay, so this happens when x implies, let me do it in black, it's not here. Okay, so this happens when x is equal n times pi over k. And if I put instead of k, so n times pi divided by k is 2 pi over lambda. So this will give me pi and pi will cancel out, and lambda over 2, where n is equal 1. It can also be 0, 1, 2, 3, 4, etc. Okay, and these points we said we call them nodes. Then there are the points that oscillate with maximum displacement, so maximum amplitude. This happens when sine kx is equal n pi over 2. Or another way to say it, it's when kx is equal to n plus 1, because we want to guarantee that we have a like 1, 3, 5, 7. Okay, so 2n plus 1 pi over 2, where n is equal 0, 1, 2, 3, etc. Which means x equal, this happens when x is equal to n plus 1 lambda over 4. Okay, so at these positions we will have maximum displacement, like here, like here, like here. Okay, we see maximum displacement like here. This is here maximum displacement. So these happen at x equal to n plus 1 lambda over 4, like here. Okay, and the nodes happen when there is no movement at all. So these happen here. So this is here a node, and this is here called an antinode. Okay, the opposite of a node, it's an antinode. Another important thing here is that we calculated the difference between the distance, between a node and a node. The distance between a node and a node is lambda over 2. The distance between a node and two antinodes is also lambda over 2, but the distance between a node and antinode is lambda over 4. The last idea in this lesson is waves under boundary conditions. Okay, here the boundary conditions are that I have a string. Let me just change the color. So I have a string, okay, fixed at both ends. That is, I cannot move it here and here. So here and here we already have nodes. We will call it n. Okay, so here I have a node and here I have a node. Now, what are possibilities for standing waves? One of them is this, to have only one standing wave. Okay, in this case, L, which is the length, is the distance between the two nodes, which is lambda over 2, right? Implies here lambda is equal to L. The other option is if I have to, you have to excuse my drawing. Okay, so if I have to, so here the L is equal, the length is equal to lambda over 2, because I can draw two, each the distance from this node to this node is lambda over 2 and another lambda over 2, so 2 lambda over 2. So implies lambda is equal to L over 2. The first one is 2L over 1. Then the third one, let's see what if we can draw it properly. Okay, almost. Okay, so again, the lambda here is equal 3 lambda over 2, implies lambda is equal to L over 3. Okay, so etc. If I have, so here I have one loop, here I have two loops, here I have 3 loops. In general, if I have n loops, I will have L is equal n lambda over 2, and I will have lambda equal to L over N. Okay, now we said that if it is one loop, we call it first harmonic. Two loops, we say it is second harmonic. Three loops, it is third harmonics. N loops, it's N harmonics, etc. Now, how to get this equation of a frequency if I have lambda? I have to remember that V is equal to lambda times frequency, okay? So frequency is equal V over lambda, which is equal V over, how much is lambda? It is 2L over N. So this will give me, so over N. So F is equal N over 2L times V, which is N over 2L times the square root of T over mu if I have the tension and the mass per unit length. Okay, and this is how we derive this equation. Let's do one exercise. So a string, this is here lecture 16. So a string with mass density of 4 times 10 power minus 3 kilogram per meter. So I have the mu 0.004 kilogram per meter is under tension equal 360 Newton and is fixed at both ends. So we have this situation where we have boundary conditions. One of its resonance frequency, so one of the FNs is 375, but I don't know which N. The next, the higher resonance, so this is F of N. This is F of N plus 1. It's equal 450 Hertz. Okay. Here I have to remember that 375 is equal N times F1, because if you go back, Fn, let me do it quickly here. I forgot to remind you. So Fn, we got that it's equal to N over 2L square root of T over mu. But this thing, which is 1 over 2L square root T over mu, is nothing but F1. So this is N times F1. Okay, that is the first harmonic. So 375 is N times F1, and 450 is N plus 1 times F1. Okay, this is given. What is the fundamental frequency? The fundamental frequency is F1. Okay, so here I will just remove the brackets. So I will get N times F1 plus F1. Okay, and this is equal, N times F1 is 375 plus F1. So now I have 450 is equal 375 plus F1 implies F1 is equal to 450 minus 375, 75 Hertz. This is part A. Now, part B, which harmonics are the ones given? Which harmonics are the ones given? So we will say 375 equal N times 75 implies N is equal 5 implies fifth harmonic. And if this is the fifth harmonic, 475 is the second one, is sixth harmonic. Okay, part C, what is the length of the string? I will be applying one of these formulas. I can use F1, F5, F6. The easiest one is to use F1. F1 is 1 over 2L square root of T over mu. I will just put numbers. F1 is 75 is equal 1 over 2L square root of T is 360 divided by mu 0.004. 75 times 2L, it is 150. L is equal square root of 360 divided by 0.004 is the 300. implies L is equal to 3. Okay. A string 3 meters long and fixed at both ends. So again, it is a string. I have the L this time. It is fixed at both ends. So also we have boundary conditions. It is in the third harmonic. So N is equal to 3. The maximum displacement of any point on the string is 4 millimeters. So I have A is equal 0.004. The speed of transverse waves on this string is 50 meters per second. So I have V is equal 50 meters per second. What is the wavelength and the frequency of this wave? Here you have to remember that I have 3 loops implies L is equal 3 lambda over 2 implies lambda is equal to L over 3, which is 2 times 3 over 3, which is 2 meters. Okay, and we have to write the wave function for this wave. Y is equal amplitude, which is 0.004. Okay, sine K. So for the standing waves, it is A sine KX cosine omega t. So Y is equal A, which is 0.004. Sorry, here I forgot to calculate the frequency. Frequency is V, or you start with V is equal lambda times F, implies F is equal V over lambda, which is equal 50 over 2, which is equal 25 meters per second. So this is 0.004. Sine of K is 2 pi over lambda, which is 2, times cosine omega, which is 2 pi F, which is 25 T. So Y, this is here X. So Y is equal 0.004 sine X cosine 50 T, 55 T. And this is pi X. Okay. You need to memorize the formula for the standing wave. It is Y equal A sine KX cosine omega T. The last exercise. A standing wave on a rope is represented by the following wave function. So this is the standing wave function. They are giving me the function. Write the wave functions for the 2 traveling waves that when superimposed will produce the resulting wave pattern. Here I have to remember that Y1 will be equal to, we have to remember that Y resultant is 2A sine KX cosine omega T. So Y1 is 0.01 sine pi X over 2 minus 40 pi T. Okay, and Y2 is 0.01 sine pi X over 2 plus 40 pi T. Okay, so what we did here is just what we did with the standing waves. Standing waves, if I have Y1 equal A sine KX minus omega T, Y2 is A sine KX plus omega T, I get the resultant to be 2A sine KX cosine omega T. So if I have this, how to go back? I divide by 2 to get the A, and then I just put sine KX minus omega T, and the other one plus omega T. Okay. What is the distance between the nodes of the standing waves? So this is part A. What is the distance between the nodes? So here you have to remember that distance between a node and a node is lambda over 2. How much is lambda? It is 2 pi over k over 2. The 2 and the 2, they cancel. And I will have pi over k. So pi over, how much is k? K is pi over 2. Is equal to meters. Okay. Here they can also ask me find the distance between a node and antinode. So I would say it is lambda over 4. Find the distance between the first node and the third antinode. So I have to calculate this distance by saying, okay, first I go to from one node to the second node, then to the third node, then to the antinode. So it will be like 2 nodes plus quarter over 4, something like that. Okay, we will solve something like that during the live session. So that's it for today's lecture. If you have any questions, just send me an email so as we can cover it during the next live session, because this lesson is included in the example. So for now, bye-bye.